Hey everyone, in this video we're going to go over section 3.5, Implicit Differentiation. So, up until this point we've always taken the derivative of functions where y can be described explicitly as a function of x. Like y is some function of x that's equal to the square root of x squared plus 1. Y is explicitly described. Or we could have, say, y is equal to x times the sine of x. But for some functions, y isn't explicitly defined. It's defined implicitly, kind of like x squared plus y squared is equal to 25. And how we can't solve for y by itself. We would get two equations. Y is equal to either the positive square root of 25 minus x squared, or y is equal to the negative square root of 25 minus x squared. And so if we wanted to calculate the derivative with respect to y, we would get one derivative here, and we would get one derivative here. But what we want to do is we want to start off with an equation, x squared plus y squared is equal to 25. And we want to do something. We want to take derivatives, and that's what we're going to do. We'll take derivatives. And what we want to be able to do is we want to come out with some statement about the change in y with regards to x. The thing to remember here for this entire section is that y is a function of x. It is not a constant. So that means the derivative with regards to x of y is equal to the derivative of y with regards to x. So we're going to be doing things like taking the derivative with regards to x of y squared. This is going to just be a chain rule where we take the derivative of the outside, the power is going to come down, 2, the inside is going to stay the same, our exponent is going to be subtracted by 1, times the derivative of the inside, which is going to be dy dx. This isn't necessarily too enlightening without context. We're going to do this right here in a moment. But I wanted to say that. Thing to remember is y is a function of x. That's the first thing to remember. And the second thing to remember is that the derivative of x with regards to y is just dy dx. And implicit differentiation really is just the chain rule. Just kind of a more generalized version. So, let's begin with example 1. So, example 1 says if x squared plus y squared is equal to 25, we want to find dy dx. That'll be the first thing we do. And the second thing we do is we will find the equation of the tangent line. Find the equation of the tangent line to the circle. X squared plus y squared is equal to 25 at the point 3, 4. So that's what we're going to do. We're going to find dy dx, given that, and we're going to find the equation of the tangent line to that circle. Okay, so we'll set this up. So we have x squared plus y squared is equal to 25, and I left a gap there on purpose. What we want to do is we want to go through, well, if these two things are equal, that means their derivative with regards to x has to be equal. We're taking the derivative of the left-hand side, that's equal to the derivative of the right-hand side. Derivatives can distribute over addition and subtraction, so we get the derivative with regards to x of x squared plus the derivative with regards to x of y squared is equal to the derivative with regards to x of 25. Well, the derivative with regards to x of x squared, that's going to be 2x. Plus, this is going to be our chain rule. We get 2 times y times the derivative of the inside, dy dx. And that's equal to the derivative with regards to x of any constant is 0. Well, the thing that we're after is dy dx, and here it is right here, so let's solve for it. At this point, we're done with calculus. Now it's an algebra problem. This is the thing we want, let's solve for it. I'm going to subtract 2x from both sides to get 2y dy dx is equal to a negative 2x. I want dy dx, I can divide both sides by 2y. And we get dy dx is equal to negative 2x divided by 2y. Those 2's will cancel, and we're left with negative x divided by y. So how much y is changing depends on the ratio of negative x to y. Perfect. So this is still the slope of the tangent line. Except for now, it depends on a value of x and a value of y, which should make sense because if we're on a circle, this x-coordinate corresponds with 2 different y-coordinates. And so we need to know the value of y to know if we want that tangent line or if we want that tangent line. So to find, and this is A, to find B, do I have a backside? I do not. For B, well, we need the equation of a line. Lines have two things. They have a slope, and they have a point. The point has been given to us. That's the point 3, 4, and the slope is left to us to find. Well, the slope is going to be equal to the derivative of y with regards to x. And you might see this notation. The derivative of y with regards to x evaluated at the point 3, 4. I don't use this notation a lot, but I want to remind you that it exists. That's equal to negative x divided by y. Or, written together, we get slope is m, which is equal to negative 3/4. So we want the equation with that slope that goes through that point. We want to fill out the equation y minus 4 is equal to m times x minus x. Y minus 4 is equal to negative 3/4 of an x plus 9 on 4. Y is equal to negative 3/4 of an x plus, negative 4 is negative 16/4. 16/4 plus 9/4 gives us 25/4 as a final answer. Really, the only thing new, we've done B, the only thing that's different is that our derivative looks different now. Really, this section is more about implicit differentiation. We know that this left-hand side is equal to that right-hand side. That means the derivative of the left-hand side has to be equal to the derivative of the right-hand side. We're taking the derivative with regards to x of x squared. That's just a plain old derivative. But when you take the derivative with regards to x of y, well, y is a function of x. This is our chain rule. you can think of it, and I'll write down here so we don't get too messy. When we're taking the derivative with regards to x of, and I have it written as y squared, that's the same thing as taking the derivative with regards to x of some composition of functions, oops, messed that one up, equal to the derivative of a composition of functions where f of x is equal to x squared and g of x is equal to some function y as a function of x. So f prime of x is equal to 2x, and g prime of x is equal to, well, the change in y with regards to x. So by our chain rule, the derivative with regards to x of y squared is equal to f prime of g of x times g prime of x. Well, that's going to be f prime is 2 times g of x. We typically don't write y of x, we just write y times the derivative g prime of x, dy dx. So this step kind of goes in between that step and that step. Whenever we take the derivative with regards to x of y's, use the chain rule. Whenever we take the derivative with regards to x of x, take a normal derivative. The derivative with regards to x of any constant is equal to 0. After this point, it turns into an algebraic exercise, and you're left with solving for dy dx. Once you get here, what we've done should take over. Alright, so let's do example 2. What example 2 says is, the first thing we want to do is we want to find y prime if x cubed plus y cubed is equal to 6xy. Okay, so the thing to remember is that y prime is just another way of writing dy dx. So if we want to find y prime, that's the same as finding dy dx. And in fact, some books, some people, they go through, instead of writing, I gotta find it, right here, how I call the derivative of, well, we can go back here. The derivative of x of y is equal to dy dx, which is also the same as y prime. There we go. I'll add that. So, it goes like that, and this goes like that. So if we want to find y prime, well, that means we want to take the derivative of the left-hand side, and that's going to be equal to the derivative of the left-hand side. Derivatives distribute over addition. And constants can be pulled out. Remember, y is a function of x, so y can't come in front of the derivative. And, for good measure, we should put parentheses around y and x. Now we actually go through and we take the derivative. The derivative, and I'm going to shift slide to the left, the derivative with regards to x of x cubed is 3x squared. Plus, this is going to be a chain rule. This is like the derivative with regards to x of y cubed. This is our power rule mixed with a chain rule. Bring our power down, 3 times the inside, subtract 1 from the power, times the derivative of the inside, which, for this problem, instead of writing dy dx, I'm going to just call it y prime. and that's going to be equal to 6 times. Now over here what we have is we have a product. When we go to take the derivative of a product, we need to use the product rule. So what that says is the derivative of the product is equal to the derivative of the first times your second plus your first times the derivative of your second. And the derivative of y is either dy dx, or we're calling it y prime in this problem. That's it. At that step, you're done with calculus. The next thing you want to do is you want to solve for y primes. It's tricky. We've got one over here, and we got one over here. At some point, we're going to have to probably do some factoring and use some division. Yeah, that's right. So, I'm just going to simplify. 3x squared plus 3y squared y prime is equal to 6y plus 6xy prime. I want to solve for y prime. I'm going to get them both on the same side of the equation, move everything else over. I would get a 3y squared y prime minus 6xy prime is equal to 6y minus 3x squared. We can factor out a y prime. Y prime times 3y squared minus 6x is equal to 6y minus 3x squared. Divide off 3y squared minus 6x. 3y squared minus 6x to get y prime is equal to 6y minus 3x squared all over 3y squared minus 6x. All of these coefficients are divisible by 3, so I will call that 3 times 2y minus x squared divided by 3 times y squared minus 2x to get y prime is equal to 2y minus x squared divided by y squared minus 2x. Y prime, same as dy dx. This problem, there's two new things going on in this problem. One, we're introducing this idea that x times y, this is a product of either of x and functions of x. You're going to have to use the product rule. And still we're applying this chain rule. This problem looks different because we've gone through and we've used a y prime. Remember, calculus was developed by different people at the same time. They developed their own notation. And a lot of what this book is trying to get you guys used to is the fact that there's different notation for conveying the same idea. So we're using different notation for conveying the same idea. And we get the change in y. This is, after all, the change in y with regards to x is equal to that. Perfect. So let's go on to a part B and C. Okay, so I forgot to write it at the beginning, but for part B, what we're going to do is we're going to use our new derivative, y prime, to y minus x squared all over y squared minus 2x, and that's a y. And what we want to do, and that's a b, we want to find the equation of tangent line at the point 3, 3. So, you've got a point, we need a slope. Our slope is going to be equal to the derivative evaluated when x is equal to 3 and y is equal to 3. So we get 2 times 3 minus 3 squared all over 3 squared minus 2 times 3, which gives us 6 minus 9 for a negative 3 divided by 6 take away, I'm sorry, 3 squared is 9, not 6. Take away 6 over a positive 3, which gives us a slope of negative 1. So we want the line that goes through the point 3, 3 with slope negative 1. Which gives us y minus 3 is equal to a negative x plus 3, or y is equal to a negative x plus 6. This line is tangent to this curve at that point, and the slope of this line was given by that derivative. Got things going all over the place. Cool, let's do B. Now let's do part C. So what part C says, I've covered up my notes. What part C wants us to do is find at what point in the first quadrant let's see, at what point in the first quadrant is the tangent line horizontal? Oops, that was lean. At what point in the quadrant, in the first quadrant, is the tangent line horizontal? Well, as a refresher, the first quadrant of a graph is up here, where we have a positive value of x and a positive value of y. So, sorry, I have a bee flying around now. So we want to figure out where in the first quadrant has a horizontal tangent line. That means we want to take the derivative, y prime being equal to 2y minus x squared all over y squared minus 2x. You'll have to excuse me. Sorry about that. So, like I was saying, at what in the first quadrant? We need the word point. I'm sorry. There's a bee flying around. It was distracting me. It's technically a wasp. At what point in the first quadrant is the tangent line horizontal? Okay. Then I told you, or reminded you, that the first quadrant is over here where we've got a positive x coordinate and a positive y coordinate. It's like the point 1, 2 for the sake of argument. Where has a horizontal tangent line? Well, that means what values make that derivative equal to 0. Fractions are equal to 0 when their numerator is equal to 0. Or we see solving for y, that happens when y is equal to a half of x squared. Provided that y squared minus 2x is something different than 0. So any value that satisfies this relationship will give us a horizontal tangent line. What we want to do is we want to find every value on the curve, x cubed plus y cubed is equal to 6xy. That satisfies this relationship. Or in other words, we want to restrict this curve to only give us values that also satisfy that relationship. Plus, y is equal to 1/2 of x squared, then we have is equal to 6 times x times y, which is 1/2 of x squared. And that should be cubed. Perfect, the original, and I was looking off screen, it was right here, I don't know why I was looking way over there. Now what we want to do is we want to find the values of x that satisfy this. Well, this gives us an x cubed plus a 1/8 of x squared. Cubed is an x to the 6th, and that has to equal a 3x cubed. Okay, going on, we're trying to solve for a value of x. I'm going to move everything to the left-hand side of the equation. This will give us an 1/8 of x to the 6th minus 2x cubes. Gotta equal 0. Fractions are hard. Multiplying both sides by 8 gives us x to the 6th minus 16x cubed is equal to 0. Factor out an x cubed. X cubed times x cubed minus 16 is equal to 0. Zero product rule, that either means x is equal to 0 or x cubed minus 16 is equal to 0. This means x is equal to 2 to the 4 thirds, because 16 is equal to 2 to the 4th, and then we took the cubed root of both sides. Thing to remember, we only want the values of x that are positive. 0 is not positive, so the only positive value of x that satisfied this relationship was 2 to the 4 thirds. But we're looking for a point. Points have an x coordinate and a y coordinate. So, two things to remember. Either you can either plug x into the original, or you can plug this value of x into this equation. Both of them will give you the value of y. This one will be harder to solve for. So, if y is equal to 1/2 of an x squared, and x is equal to 2 to a 4 thirds, that means y is equal to 1/2 of a 2 to a 4 thirds squared. That's equal to 1/2 of 2 to the 8 thirds, which is equal to 28765. 2 to the 5 thirds. Because remember, dividing by 2 is the same as multiplying by 2 to the -1, and we add our exponents. That gave us the point 2 to the 4. That wasn't a 4. That wasn't even kind of a 4. 2 to the 4 thirds. 2 to the 5 thirds. It's the only spot on this curve that's in the positive first quadrant, or in the first quadrant, that has a horizontal tangent line. So, looking over what we did, the first thing we wanted to do is find y prime. So, in order to find y prime is the same as dy dx. Well, if this statement is true, if x cubed plus y cubed is equal to 6xy, then that means the derivative of both sides have to be equal. Derivatives with regards to x of just x's works normal. Derivative with regards to x of y is a chain rule, which is why we brought that power down, left the inside alone, subtracted 1 from the power, and times the derivative of the inside. That was equal to 6. When we have x and y together, you have to use a product rule. So we use the product rule. The derivative of our first times our second plus our first times the derivative of our second. After that step, we're done with the calculus for part A. We have to go through and we have to solve for y prime. Y prime, after all, is just dy dx. We found y prime. Part B was find the equation of a line at a slope. Now, you shouldn't be surprised when your dy dx's, they have x's and y's floating around in them. So, they give us a value of x and y. We plugged them both in. This is just me using more notation, trying to get you guys used to the fact there's a lot of different ways of doing the same thing. So, I used this notation. This says the derivative of y with regards to x evaluated at the point 3, 4 is equal to -3/4. Perfect. Calculus is done, just doing algebra now. Equation of line with that slope through that point. Then, we moved on to part C. So at what point in the first quadrant, that was important, is the tangent line horizontal? Reminded you that the first quadrant has a positive x and positive y value, and when a tangent line is horizontal, that means the derivative is equal to 0. Well, fractions are equal to 0 when the numerator is equal to 0, and we came up with this relationship. We wanted all the values of x and y that satisfy that relationship that also lie on this curve. So we plugged this relationship into our original curve, and we came up with some values of x. Either x was equal to 0, which we disregarded because 0 isn't in the first quadrant, or x is equal to 2 to the 4/3. That's a positive number, that's in the first quadrant, this is the only value we took. Okay, then we had to figure out, and where did I go from here? We had to figure out, is asking at what point, points have x coordinates and y coordinates, so we needed to figure out what y coordinates corresponds with this x coordinate. There was one of two ways. One way, we could have tried to plug it back into the original. That would involve factoring a cubic. That can be kind of difficult. The other way was we had this nice easy equation that was a rule for relating the values of x to y. We restricted all of our values of x that we could get from this equation to the values of x we could get from this equation. So any value of x that we get from here has to satisfy this, meaning we can plug that value of x into that thing, and we get a value of y. So, you guys will be asked to do this on your homework. You guys will really be asked to do this. You'll have to do this part C, where you take a derivative, set it equal to 0, come up with an equation, plug it back into the original, get a value of x. Perfect. Let's move on to example 3. So example 3, and I think all we're doing is just finding, we're just finding y prime. So find y prime, provided that that the sine of x plus y is equal to y squared times the cosine of x. Okay. So, if the sine of x plus y is equal to y squared times the cosine of x, that means the derivative of the sine of x plus y is equal to the derivative of y squared times the cosine of x. Okay, so you could use a trig identity and break that up if you want to. I'm not going to. The derivative of the left side, this is a chain rule, we get the derivative of the outside, the derivative sign is cosine. The inside doesn't change, x plus y times the derivative of the inside. The derivative of x is 1, and the derivative of y is just a y prime. Once again, I could have used dy dx, but we're solving for y prime in this problem, so I'm just going to use that notation. If it said dy dx, I would have put a dy dx right there. So this is our left-hand side. By our chain rule, this is what we get. That has to be equal to the derivative of the right-hand side. The derivative of the right-hand side, the first thing we're going to do is a product rule. And then the kind of part A of the part 1, or step 1 of the right-hand side is product rule. Part 1A is going to be a chain rule. So we're not doing too much at once. I'm just going to write this. So we take the derivative of our first times our second plus our first times the derivative of our second. So going from here to here, that was a chain rule. And going from here to here, that was a product rule. This left-hand side, I'm just going to rewrite. Cosine of x plus y times y plus 1 plus y prime. And that's going to be equal to, this is a chain rule, power comes out, 2y, 2 take away 1 is 1, times the derivative of y, which is y prime, times the cosine of x, plus y squared is going to drop down. The derivative of cosine is a negative sine of x. Perfect. So now we're trying to solve for y prime. There's one there, there's one there. I'm going to move this over and leave that alone. So that turns into a cosine of x plus y times 1 plus y prime minus 2y prime cosine of x, and that's going to be equal to, that minus sign is going to come out front, and we're going to get a negative y squared sine of an x. Awesome. So I'm going to distribute this cosine of xy through, get a cosine of x plus y plus a y prime cosine of x plus y minus 2y prime cosine of x minus y squared sine of an x. Oh, on the final step on this page, I'm going to move this cosine to the right hand side to get a y prime times a cosine of an x plus a y minus a 2y prime times a cosine of an x. And I forgot to write my equal sign going between these two lines, so I'm going to put my equal sign, do it in a different color, right here. I just forgot to copy that down. So this is going to be equal to negative y squared times the sine of x minus the cosine of x plus y. Let's get a new piece of paper. So I've got a y prime here and here. I'm going to factor it out. Give us y prime times, we've got a cosine of an x plus a y minus 2y times a cosine of an x, and that's going to be equal to a negative y squared sine of x minus a cosine of an x plus a y. We're going to divide off everything we don't want. From both sides. I'm scared of covering up my autofocus zebras. Cosine of x plus y minus 2y cosine of an x, y prime is equal to that thing. Negative y squared sine of x plus a cosine of an x plus a y. I said plus, it should have been a minus. I'm thinking of what I'm going to do next. All divided by a cosine of x plus y minus a 2y cosine of x. So I'm actually going to factor out, and this is a good spot to stop. I typically don't like minus a minus in my numerator. It's personal preference, and I think it's good to show you where the book gets its answer. Y squared sine of x. Factor a minus sign out of that negative became positive. Factor a minus sign out of that negative becomes positive. And if we factor a minus sign out of the denominator, well, that was negative, so it'll go positive. And that was positive, so it'll go negative. These minus ones will cancel. And the answer that we get, the answer that the book gets, is y squared times the sine of an x plus the cosine of x plus y divided by 2y cosine of x minus the cosine of x plus y. Perfect. So we have now found y prime. And that's all we were doing for this problem. This started off as, I believe, example 3. So we started here. Okay. So taking the derivative. We've got a chain rule over here, and we've got a product rule with a chain rule over here. You're fine. So we applied our chain rule. Derivative of the outside doesn't change the inside times derivative of the inside. And whenever we take the derivative of y, we get a y prime. Keep walking. Then we took the derivative of the right-hand side. To take the derivative of the right-hand side, we had to use this product rule. We're taking the product of two things. So we did the derivative of our first times our second, plus our first times the derivative of our second. Oh, come here. Derivative of first times second plus first times derivative of second. And then we were just simplifying. We were trying to find y prime. A lot of times in this problem we're going to have a bunch of y primes floating around, and it's going to be left to you guys to figure out the algebra needed to isolate y prime. We're just trying to solve for this variable. After this step, all the calculus is done. The last bit of calculus comes over here where you confidently say what y prime is. But really, after this line, or from this line down to over here, it's an algebra exercise. Just trying to get y prime by itself. Big takeaways. Chain rule. Product rule. Y squared times cosine of x. You've got to use the product rule on that. And don't forget these chain rules. Whenever you have a y floating around, you need these chain rules. Let's go and do example 4. Okay, example 4. So now, we're going to find y double prime, which is the same as finding the second derivative of y with regard, to x. Okay. So, lost it. So we're going to find y double prime if x to the fourth plus y to the fourth is equal to 16. Okay. So the first thing, well, we want the second derivative. We're going to have to take the first derivative of x to the fourth plus y to the fourth equals derivative with regards to x of 16. Derivatives distribute over addition. Derivative of x to the fourth is 4x cubed plus derivative of y to the fourth. This is a chain rule. That'll become 4y cubed times y prime times a change in y with regards to x. And that's equal to the derivative of a constant. Well, solving for y prime, we get 4y cubed y prime equals negative 4x cubed. Divide 4y cubed, divide 4y cubed. Cancel, cancel. Those two also cancel. Y prime equals negative x cubed over y cubed. You can call it whatever you want to. You could factor out the cube and call that negative xy quantity cubed. I'm going to leave it like that. So this is y prime. The thing to remember about y double prime, well, that's equal to the derivative with regards to x of y prime. Well, that's going to be equal to the derivative with regards to x of negative x cubed over y cubed. This is going to be a quotient rule. Like I was saying before, don't think of your chain rule, your product rule, and your quotient rule as a way to solve a problem. Think of your chain rule, your quotient rule, and your product rule as a way to solve a step. And now the problems are just containing more steps. Want to take the derivative? That's going to be equal to low times the derivative of the top, negative 3x squared, minus the top, times the derivative of the bottom, 3y squared, times the derivative of the inside, y prime, all divided by the denominator squared, y cubed quantity squared. So perfect, I wanted to do this on another page. So we get y double prime being equal to, I'm going to simplify this minus sign and that minus sign. I'm going to call this negative 3x squared y cubed plus 3x cubed y squared y prime, all divided by y to the sixth, which is a very true statement. The thing to remember is that we already know what y prime is. It's right here. So let's do this substitution. Y double prime is equal to, y double prime is negative 3x squared y cubed plus 3x cubed y squared. Y prime is negative x cubed over y cubed, all divided by y to the sixth. Now she's bugging my other cat. That's moderately better. So now we're just simplifying. This is equal to negative 3x squared y cubed. Oh, and then we'll do this. Plus 3 minus 3x to the sixth y squared over y cubed all over y to sixth. These will simplify. That'll go to a 1. That will go to a 1. And this is equal to negative 3x squared y cubed minus 3x to the sixth over y divided by y to the sixth. If I multiply top and bottom by y, this will be equal to negative 3x squared y to the fourth minus 3x to the sixth all over y to the seventh. And then the book goes through. Cool, we can do that too. Y double prime is equal to, they pull out a negative 3x squared, they leave the x squared in. Negative 3x squared y to the fourth minus x to the sixth all over y to the seventh. You could have stopped here. As far as I'm concerned, I do not like compound fractions. So you can stop once you are done with the compound fraction. Let's shift gears and move on to something else. Sorry about that. So we wanted to find the second derivative of y with regards to x for this problem. So, like we have done, we've taken the first derivative, remembering that the derivative of things with just x's is a plain old derivative, and the derivative of things with y's is a chain rule. Derivatives of constants are still constants. Solving for y prime, figured out what y prime was. Wasn't our goal, but was a necessary step to get to our goal. Well, we've got the first derivative. The derivative of the derivative is equal to the second derivative, so we took the derivative right here. We did low times the derivative of the top, minus, and then the top, and that's why that minus sign became a plus, the derivative of the bottom, which was a chain rule, all divided by the denominator squared. Had to use the quotient rule here. After that, it was some simplifying. We knew what y prime was. We don't necessarily want to have the value of the second derivative in terms of the first. That's starting to get into the realm of differential equations. So we knew what y prime was, so we did that substitution. Y prime was negative x cubed on y cubed, And then we don't like compound fractions. We went through and we simplified our fractions. I would have stopped here. The book chose to stop there. I thought it was odd that the book didn't pull out an x squared. I'm not concerned with your answers being identical to the answers in the back of your book. I'm more concerned with the work that you did to get to that answer. Don't be afraid if your answers don't match the ones in the back of the book exactly. They should be algebraically equivalent. These two are algebraically equivalent, but they don't need to be identical. So let's shift gears and do something similar but different. We'll talk about the derivatives of inverse trig functions. So, for example, if we said y was equal to the sine inverse of x, what's that telling us is that the sine, that's an arrow, the sine of y is equal to x. And if the sine of y is equal to x, and that means the derivative with regards to x of the sine of y has to be equal to the derivative with regards to x of the derivative with regards to x of x. Well, what this says is, by the chain rule, the derivative of the outside, cosine with the inside, times the derivative of the inside has to be equal to the derivative of the right-hand side. We want to know what y prime is, or we want to know what dy dx is. We'll solve for it. Y prime is equal to 1 over the cosine of y. Now, what this statement right here says is, if we have a right triangle, that angle is y. The sine of y, which is the opposite over the hypotenuse, is equal to, what this statement is saying is that the sine of y being equal to x is that this side length of the triangle is x, this side length of the triangle is equal to 1. We can use a Pythagorean identity saying that a squared plus b squared is equal to c squared, or in this problem we would get, I'll write that out, a squared plus b squared is equal to c squared. We want to know the value of a, so that's saying a squared is equal to c squared minus b squared, or a is equal to the square root of c squared minus b squared. And for this kind of mini problem, that means a is equal to the square root of 1 minus x squared. So we get a, or this side length, being equal to the square root of 1 minus x squared. And then when we want to take the cosine of that angle y, well, the cosine of y is equal to the adjacent over the hypotenuse. So this is equal to 1 over the cosine of y, which is the square root of 1 minus x squared. Or we get that if y is equal to the sine inverse of x, then the derivative of y with regards to x is equal to 1 over the square root of 1 minus x squared. I'll do another one of these. Let's say we have y is equal to the tan inverse of x. Well, that means the tangent of y has to be equal to x, which means that the derivative with regards to x of the tangent of y has to be equal to the derivative with regards to x of x. The derivative of tangent is secant squared, so we get the secant squared of y times the derivative of the inside has to be equal to the derivative of the right-hand side. Dividing a secant squared off, we get y is equal to 1 divided by the secant squared of y. Oh, and I'm just seeing what direction the book goes with it. We can do that. So, we know that, and now we'll have to do some trig, that if the sine squared of an x plus the cosine squared of an x is equal to 1, we can divide both sides of this equation by a cosine squared of an x and a cosine squared of an x. Sine squared divided by cosine squared gives us a tangent squared of an x, plus cosine squared divided by cosine squared is 1, and that's equal to a 1 over a cosine squared of x, or 1 over a secant squared of an x. So, this y, and this should actually be a y prime because I solved for this y prime is equal to 1 over, instead of a secant squared of x, I'm going to write a secant squared of y, I'm going to write a tangent squared of a y plus 1. But we know what tangent of y is. Tangent of y is x, so that means that tangent squared of a y is equal to an x squared plus 1. Or we get that the derivative with regards to the derivative of y with regards to x of the tangent inverse of x, some people would call that the arctan, is equal to 1 over x squared plus 1. So we're using we're using implicit differentiation to come up with these. Following this example, how we let y be equal to the sine inverse of x, and that means that, and then we go through and use implicit differentiation, sometimes a triangle as need be, we can derive the following. The derivative with regards to x of the sine inverse of an x is equal to 1 over the square root of 1 minus x squared. The derivative with regards to x of the cosine inverse of x is equal to negative 1 over the square root of 1 minus x squared. The derivative with regards to x of the tan inverse of x is equal to 1 over 1 plus x squared. The derivative with regards to x of the cosecant inverse of x is equal to negative 1 over x square root of x squared minus 1. Derivative with regards to x of the secant inverse of x is equal to 1 over x square root x squared minus 1. And derivative with regards to x of the cotangent inverse of x is equal to a negative 1 over 1 plus x squared. Wonderful. These are our 6 new derivatives. They are identities. You guys can jump from here to here freely without having to derive them every time. You might have been derived to ask some of these on your homework. And we're really just going to use these as rules for differentiation. So, if we knew that y was equal to 1 over the sine inverse of x, and be careful because that is not the cosecant inverse of x. We want to find its derivative. Well, we need to use a quotient rule. Y prime is equal to low times the derivative of the top, the d dx of 1, minus our top times the derivative of our bottom, all over our denominator squared. I would not call this sine to the negative 2 of x. I would call this the sine inverse of x squared. This is actually why I try and say arcsine. I fail at it most of the time, but why I want to call this arcsine, because the arcsine squared is not ambiguous, but sine to the negative 2 of x could be. So, y prime is equal to derivative of any constant is 0. So we get 0 minus, so we'll get a negative here. The derivative of sine inverse of x is negative 1 over the square root of 1 minus x squared. This is our numerator. This is still divided by our denominator. This is a compound fraction. We don't like those. We can multiply top and bottom by the square root of 1 minus x squared over the square root of 1 minus x squared to get y prime being equal to negative 1 over the sine inverse of x quantity squared times the square root of 1 minus x squared. Perfect. You guys go off and find y double prime. So this is really implicit differentiation. The big things, the big takeaways are y is a function of x. The derivative with regards to x of y is equal to dy dx. For a lot of examples, we just called that y prime. Potato, potato. You have to use the chain rule for stuff like the derivative with regards to x of y squared. That becomes 2y y prime, or 2y dy dx. Once again, potato, potato. Whenever you go and take the derivative of something nice, and what do I mean by something nice? I mean something like this. We're taking the derivative with regards to x of x. These derivatives behave normally. But when you take the derivative with regards to x of y, you have to remember the chain rule. Power comes down, minus 1 from power, derivative of inside. Derivative of constants is just 0. This section has a lot of algebra solving for y prime, has a lot of algebra solving for dy dx. Remember, they mean the exact same thing. The book is going to throw them both at you, trying to get you used to the fact that there's different ways of saying the same thing in calculus. For homework, everyone's favorite part, go off and do 5 through 17 every other odd. 31, 35 through 39, odd. 43, do 49 through 57, odd. Go off and do those. Send me an email if you have any questions, and remember on that, oh goodness, where was it? Remember that when we solved for y, when we solved for y double prime, we had some stuff that had y prime in it, and we were able to substitute back in for that y prime. Send me an email if you guys have any questions. I'll see you next time. Bye-bye.